Okay, so the next, well, now there is a second. Now there is a seminar by Dr. Roberta Zambrini, who is a professor here at IFISC. She studied in Milano University, and then she did the PhD in Mallorca, then moved to Edinburgh, Glasgow University, and then she decided that Mallorca was nice enough, and she returned back, and she got a position 5 years ago.
7.
So she has worked in many aspects of optics, pattern formation in optics, nonlinear optics, quantum optics, and now she's doing something which is not specifically optics, but it's related to quantum stuff and synchronization.
Quantum stuff is a very common expression. So let's see the quantum stuff. This is a talk about synchronization. Then you can leave, eh? You cannot enter, but you can leave. So this is a work realized in collaboration with Lalo, sitting there, and Fernando, probably working in his office. Gianluca is now in Torino, and Pera Emilio, you know them well, and myself. And I couldn't attend the lessons of Arkady Bykowski during the week, but I understand that you have been learning about synchronization during the whole week. So I suppose that you are familiar with everything is in this slide. Of course, all the people of the university are, but I'm speaking for the students. And did you see this example? This is the most common, most cited picture of synchronization ever. And actually, there is a nice about it. Time to replace now. They are doing these mountains of maybe 100 or 200 of these metronomes in China. I saw a YouTube video about the extraction of this. So synchronization, what is this phenomenon? You saw the synchronization is a dynamical process of progressive adjustment of the rhythms of periodic or not oscillators that interact with each other. So the phenomenon is typically described by a set of equations in which you have some reciprocal coupling. The equations are, for instance, here we have two equations in which there is an harmonic part, maybe you cannot see, but just two coupled oscillators, they can be linear or non-linear, and under some conditions you have the emergence of this phenomenon of synchronization in spite of the difference of the two initial frequencies of the oscillators. So what this is not about, this phenomenon, the phenomenon of spontaneous synchronization, is not related to something else that is also studied in the quantum stuff, that is the synchronization, for instance, of quantum clocks, atomic clocks, that is used, for instance, in GPS, and also has nothing to do with the NTP, the Network Time Protocol, to synchronize computers. So you want your backup be consistently saved in another computer, and this is actually fundamental to having this to occur. And in these kind of problems, in which you have really synchronization in the sense of putting clocks at the same times, the spirit is different because typically you are interested in achieving this goal using the minimum resources, and you have some communication between the objects. So this is a different topic. We are not going to speak about this, but this is also something that is studied and pursued as an objective in the quantum regime. So these are also typical example of synchronization. Do you know all of them from the courses? Is this? No.
The one in the bottom right corner, no.
That one?
Process, no. Millennium, yes. Fireflies, yes.
Okay, so the Millennium Bridge, the fireflies all flashing together, the clubs, and the cells in our body, for instance, in our heart, and here Athene, the communication using also synchronization in the communication network in Athene. So these are just to remind you of what you probably been listening during the school. So the aim of this talk and of this work was to consider the phenomenon of synchronization not in the classical regime, but in the quantum regime. So to consider the phenomenon of quantum synchronization in the quantum regime, first of all, we have to decide how do we describe the phenomenon itself, because in the quantum regime, you don't have really trajectories, as you know, in quantum mechanics forbid the presence of trajectories in the phase space. So the first problem is the problem about the description. What are you going to call quantum synchronization? And related to this problem is how do you measure the presence or not of synchronization. Then there is another fundamental question, that is, which is the simplest scenario in which you can look at synchronization. Of course, you can have synchronization in classical systems, in nonlinear and chaotic systems. This is quite hard stuff to be treated in the quantum regime. And then one look for something that is more easily treated in the quantum regime. And then one question that was motivating us was to see if there was any relation with the presence of a synchronization between two objects and their capability to have larger quantum correlations. So their similarity in the dynamics can give rise to any associating quantum phenomena. So these are the kind of things we have been doing, and then we have been generalizing these kind of things also in quantum networks. So what has been done in quantum synchronization? The first works in quantum synchronization were actually related to quantum entrainment. So there are works in Hiterangi group in which they were considering spins, and in this spin there was actually an external driver, and then the synchronization is the synchronization of the spin with the external driver. So this is not a spontaneous phenomenon of synchronization. It's what is called entrainment. And this was also, for instance, considered by Shepalyansky in another setup. Here there are the tuned spin, and there is an external driver in the bosonic mode that is coupled to the spins. So here, this is the external coupling. And recently, actually, there have been several works in the direction of quantum synchronization in the situation in which you have an external driver, so in the case in which you have an entrainment phenomenon. I mentioned here one. There are actually more if you look in the archives also. There are some work that are not yet published. This was published a few months ago. So other things that have been considered in the quantum regime. So in the quantum regime, first, entrainment. So synchronization, but when you have an external driver that is giving rise to the phenomenon. And the second thing that has been studied that is related to the possibility to have synchronization in the quantum regime has been synchronization at the nanoscale, let's say. So synchronization, for instance, of nano oscillators. So there are works in which this is a theoretical work, for instance, in the group of Florian Marquardt, and they were actually considering the possibility to have synchronization between the mechanical modes of a nano oscillator. And this is another work. This is in experimental instead, but is not in the quantum regime, and it was in Michael Gibson group. So these work, let's say, are susceptible to be, these are experiments that are susceptible to be taken in the quantum regime and to show quantum synchronization. So on the quest to find the simplest possible system to look to have spontaneous synchronization, we were actually finding that it is possible to have synchronization in a system that is linear, and synchronization in these systems is principally due to the dissipation and to the coherence that you have into the system. And then you can characterize the synchronization also comparing this with the quantum feature. So the system we consider are just quantum harmonic oscillators, so just harmonic oscillators that are also linearly coupled between them. So the Hamiltonian of the system, the full Hamiltonian, is just quadratic, and the dynamics is fully linear. Okay? And of course, this is one of the basic models that you can consider. And here just a list a few cases in which you can have, at least within some approximation, as always, a description in terms of linear equations. Okay? Oops. So these are two pictures of the experiments related to the case in which you can have coupled oscillators. These are, for instance, the mechanical vibrational modes of nanosystems, or the positions of ions. So in first approximation, you can have they are coupled by Coulomb, And of course, in first approximation, you can assume that you have just for a small oscillation around their equilibrium position, you can linearize the dynamics. Okay? Even if the interaction is Coulomb, that of course is linear, but you can linearize. Okay? So this is the outline of this work. Before I will show what is synchronization in the case of just two oscillators, and then we will move to the case of networks. And there are other works that I will just mention here. And we will see that the most important feature in this process is actually decoherence. It is what is giving rise to synchronization. So the system we consider is this one. Two harmonic oscillators. Two harmonic oscillators with two different frequencies. Okay, so they are detuned and they are coupled with some coupling that we will vary to see what changes in the weak and strong coupling regime. Okay, and the two oscillators are coupled to an environment. So these are the two oscillators, and this would be schematic representation of the environment that is at temperature T. And this is the case in which there is a common environment, and this is the case in which there are two independent and separate environments for the two oscillators. Okay? And typically the idea is that if you have two systems, the two systems feel different environments, but if the correlation length into the environment is long enough, then the two units can feel something like a common environment. Okay? So this is the physics behind the distinction between common and separate environments that we will see here is a key distinction. Is actually what is giving rise to the very strong difference into this treatment. So this is the Miltonian describing the coupling of the two position of the two oscillators, x1 and x2, with the infinity of degrees of freedom that model the environment, okay, that have this capital X. So each position is coupled to the position of the environment by sign coupling small g, okay? So this is the case in which the environment is common. You have just one set of infinite modes of the environment, and in the case in which you have two, you will have two paths, so two infinite sets of modes, okay? So this is the base of what we are going to consider, and this is a system and a distinction that has been fruitful. This is actually quite cited work about the possibility to have asymptotic entanglement when you have this kind of scenario. So typically if you have an object and this is coupled to the environment, it will decohere and any quantum effect will just disappear, will just be washed out. Okay? But then when you have the two oscillators, if they are not detuned, so if they are identical and they are coupled to a common path, then you will see that there is actually 1 degree of freedom that is not coupled to the path. So there is a normal mode. So this, if the two oscillators are identical, the sum of the two positions is one of the two normal modes, and the other normal mode is the difference. So the difference is actually not dissipating into the environment. And then this gives rise to the fact that you can have asymptotic entanglement. So quantum correlation remains robust. They do not decohere into the environment. Okay? So this is actually that was reported by Paz and Roncaglia, and this is something that disappears when you have detuned oscillators. So if you have detuned oscillator, we're actually showing that the entanglement is lost unless we are not intended. There are cases in which you can have it, but you need to do some engineering of the coupling between the system and the environment to compensate for the detuning. Okay? So this is just pedagogical, so the schools just to give some a brief sketch about the methods that we use to describe this kind of systems. And typically when you have, so the generalization of a Schrödinger equation when you have a density operator and an open system is actually a master equation of this kind. So, no, sorry, it is actually a master equation that comes from this von Neumann equation. So the master equation has this structure, okay? So this would be the equation without dissipation. This is just like the Schrödinger equation, but for the density operator, and this is called the von Neumann equation. And then when you go into the regime in which you describe the fluctuations into the environment, you also have a Liouvillean term, as the guys that did the master here this year know very well. And then you have a description of this kind. once you get this kind of equation, you are able to calculate all the moments of the quantum operators that you have into your system. So you can calculate the dynamics of first order moments, second order moments, and so on. So these are the methods that you typically use to get the dynamics into the quantum regime. Okay? Now, if the states that you are considering are Gaussian, then it is enough to have first and second order moments to characterize the complete dynamic of the system. So typically you need, the higher order moments, so Q, for instance, the product of three operators, for instance, you need to calculate. It is just a different object that is coupled to the other one, but for Gaussian states, you can express this product as this moment of third order, for instance, of fourth order, as a function of the previous one. Okay? So for Gaussian states, we can actually have the full characterization of the quantum state of the system just knowing the dynamics of the first order moments and of the second order moments. And these are the objects that contain the full physics of the system. So, now that we have, let's say, something that describes the dynamics of the system, how is the case for the moments, we can see how these moments behave when we have these two oscillators that are coupled between them and dissipating into the environment. And typically this is what you have. So the red line, for instance, can be the second order moment of one oscillator, or the first order. This is just an example. And the black one is just the other. And then you see that the dynamics of the two is just a superposition of two different normal modes. You see something not very well organized, let's say, not coherent. So you have these disordered oscillations, okay? And to measure the quality of the synchronization of these two trajectories, you can use an indicator that you have been probably also seeing during the school that is just a standard way to see if two objects are synchronized. So you just calculate the correlation between these two trajectories over some interval of time. So you integrate over an interval in which there are a significant number of oscillations, and then you just calculate the average of the product of the two trajectories properly normalized. So if the two trajectories are almost identical, you would get 1, and this is the case in which you have synchronization, and if not, this go to 0. And if you leave the sign, you can have also anti-synchronization, where they are actually oscillating in antiphase, and then you have -1, okay? Then you can decide if you want to. So this kind of indicator that is a measure of the synchronization that is just based on the dynamics, let's say, of the moments of the system, is an indicator that allows you to put from one side, you look at the dynamics of the moments. And then you can compare if when there is synchronization you have or you don't have quantum correlations present into the system. More recently, there have been other strategies about the way in which you can measure synchronization, and in particular there was this work in Fazio group in Rome, and they were considering instead that synchronization was something that was present when there was some squeezing between, for instance, the position, the first and of the second oscillator. There was some squeezing between their relative fluctuations. So the fluctuation between the two. This is also another plausible, of course, indicator. The difference with that is that in that sense, you are mixing the behavior of synchronization and the presence of quantum correlation because you are using the same indicator. Okay? While in this case, you can maintain separate description about the dynamics, and then you look if there are or not quantum signature into these dynamics that you are describing. And this is what happens. So, at the beginning, you actually have that the two oscillators are just oscillating independently and are actually superposition of different normal modes, and you cannot appreciate any similarity between the two trajectories. But actually, after a while, so this is time, this is until 50, then you look again around 300, and you see that actually the oscillation of the positions of the two oscillators or of the variances of their fluctuations are actually synchronized. Okay? So we actually see that even if the system is a linear system, due to the way in which it is coupled into the environment, you can actually have some level of synchronization emerging into the system. And if you look at this indicator of synchronization that we were introducing before, you actually see that it reached, when the quality of synchronization is very good, it reached value 1. Okay? if you look when synchronization is present, depending on the detuning between the two oscillators and the strength of the coupling between the two, you find a diagram like this. So this is the detuning between the two oscillators. This is the coupling between them. And you actually have that if they are coupled strongly enough, they will actually synchronize. It's reasonable, okay? If you maintain this coupling, but you increase the difference between the two oscillators, at some points you lose synchronization. Please?
Question, if you compare this graph to the slide before.
Yes?
So here, how do you measure synchronization? Because for me, the second plot looks more like phase blocking or phase synchronization only, and not really relation.
With this kind of quantity, just normalize with it. So, yes.
I have a question also. Because in the next slide, you lose synchronization, but you go only up to 2. So you don't consider higher order synchronizations.
It's not present. We were checking what was going on there, but we were not seeing any.
The oscillators are linear, so you don't expect to have harmonics.
Yes, with harmonics, it's yes, it's something.
Not with classic.
We can speak about this later, but I would expect also that you need some linearity to have the harmonics coming out. In any case, we also checked and was not going. Okay. So that's good. So we have a common environment, we have two oscillators, and you have actually that in the blue region, you have synchronization. So the system is linear, but still you have synchronization. Now, if instead you go to the scenario in which you have separate environments, so each oscillator is dissipating independently, they are still coupled between them. In this regime, you don't get any synchronization. Even if you increase the coupling between the two oscillators, you don't get synchronization. Okay? So this is the main point. So the way in which the system is decohering into the environment is fundamental to have synchronization or not. And if the dissipation takes place independently in the first and in the second oscillator, so let's say that you have, for instance, classical, you go back to classical. You just take two linear oscillators, you put some reciprocal coupling by hand, and then you add some common noise. This is not a situation in which you would get any synchronization, even if you couple the two oscillators strongly. You need to have something in the coupling of the dissipation terms, that in this case is playing the role of the damping, that is actually inducing the synchronization. And this is rather nice, because the mechanism we look at it in the quantum regime, but it's also something that was not even discussed in the classical regime. So in the classical regime, there is no discussion. There are works in which there was a discussion about the role of a common noise, but not about the fact that when you have really a common dissipation in which you describe dissipation into a common environment, you have some other constraint in the dynamics of your system that can give rise to synchronization. And the only related stuff that I found was actually a word of Lord Rayleigh in the physics of sound that was actually mentioning the fact that it's interesting to know that when you have a dynamical systems, then you have the normal modes of this system. But when there is also friction present, the normal modes, let's say, that comes when you have frictions are not necessarily the same normal modes that you have without frictions, because the matrix of the friction can be different from the dynamics of the isolated system. So this is the only related things that I found that was in the same spirit. So this is related to the same issue. So even if you have been studying this in the quantum regime, this is actually unveiled something that can be also observed in. It's not necessarily quantum. You can also discuss it in the classical regime. Okay?
And it doesn't depend on the small g, so the temperature. In the limit of temperature going to 0, they should synchronize.
I will show a plot. Okay? I have the results, so you can show.
Classical,
you don't need to trust me. You can look at it.
Conservative, right? Classical, conservative, Newtonian.
No, this is also Newtonian. Classical, I mean, classical.
Without dissipation, no classical.
No, even with the, I mean, you can have a classical system, so you do not have a position and momentum operator, everything would commute with everything. This is classical formation. Okay. So this is the interpretation. Why do we have synchronization even if the system is linear, when the definition of synchronization is typically that you have non-linear systems, you need to have some self-sustained oscillation. So what is going on here? So the physics that is going on here is actually quite simple when you look at it, and is the fact that when you have a system and you have normal modes, if you have dissipation into separate environments, so here now these are the oscillators and these are the environments. Okay? The dissipation of this oscillator into the normal modes, the environment can be described also looking at the normal modes of the system. And when you go into the normal modes of the system, you actually see that each normal mode has a similar damping rate into the environment. Okay, so this is in the case of separate path. If you now go into the case of common bus, this is not going to happen. Typically, you have your coupled oscillators. These are coupled to a common environment, and when you go into the description of the normal modes of the system, typically you have that each one has a different damping rate. So some normal modes are more damped than some other normal modes. If you are in a situation in which you have one normal mode that is less damped of all the other, then this will survive because it will suffer less decoherence and dissipation, while the other one, all the other one will just thermalize. So at the end you will have synchronization because there is a normal mode of the system that is maintaining this oscillation. And the oscillators that are involved, that are part of these normal modes, will maintain the oscillation. And of course it's synchronization because one normal mode is just one frequency. So it's just, everything is just closed simple, okay? So the point is that when you have a common path, you have different rates. When you have separate paths, even if you go to the normal modes, the rates are all the same. And of course, one in a network case, for instance, we'll see later, one can envisage also situations that are different in which you can have the same mechanism here taking place beyond common path. So now the second part of the question. Okay, now we have a system, it's simple, it's linear, harmonic oscillator, we can do everything with them. Gaussian, we can calculate quantum fluctuation, entanglement, discord, everything we want to calculate about them. And now we want to know if when there is synchronization, we actually have some quantum features associated with this synchronization. And I do not have time to enter into the detail, but I just mentioned that we consider different indicators of quantum correlation, let's say. So we can consider just the mutual information between the two oscillators, calculated with the phenomenon entropy. We can calculate the quantum discord, that is an indicator of quantum correlation that has been proposed recently, and that is actually having quite strong success in the quantum information community. Then there is entanglement, that is just related to the non-separability of the state. So it's a property that has not a classical analog. Okay, so these are just different properties we are looking. And the other is these are kind of twin beams correlations. So it's the presence of fluctuations in the intensity of the two oscillators that cannot be explained, let's say, with any classical probability. So it's not classical in this sense. Okay, just to give an overview. So these are just all ways to characterize the quantum correlations into the system. And what we're actually finding is that, yes, when you have synchronization, you also have more robust quantum correlations. So this, for instance, let's look at the discord, is a measure of quantum correlation. So when you have a separate path, that is the case in which there is no synchronization, you see that even if you put some strong correlation in the initial state of the two oscillators, so initially you have your two oscillators and they are strongly correlated, due to the coherence, they will actually lose their quantum correlation. The state at the end will just be thermal and will just be classical. Okay? If you have a common environment, then they will synchronize, okay? And they will also maintain more robust quantum correlation. So the quantum correlation here remains high. And this is not only true for quantum correlation, it's also true for the mutual information and also for other indicators that we are considering. not for entanglement. Entanglement is fragile. Entanglement is just lost, typically. Okay? If you now look at the case of common paths, in which we know that for some parameters we have synchronization, we actually see that in the region in which there was synchronization is also the region in which asymptotically you have stronger quantum correlation. Why? For common path, but in a parameter region in which asymptotically there was no synchronization, also you don't have any quantum correlation. Okay? So the synchronization seems to be actually here quite well related to the presence of more robust quantum correlation. Temperature. So this is just looking at the difference when you have increasing temperature, and you actually see that the feature of the system, the behavior of the system is qualitatively present also in this case, being mainly the difference about the fact that, of course, a higher temperature state will have less correlation present, so it will be just lower, okay? But the shape of the decays of the correlations in the case of separate paths or in the case of common path is qualitatively the same. So it's not that it's not depending on temperature, but that it's qualitatively present with the same behavior also when you increase the temperature. Okay? So the fact that here you have a plateau and here there's something that decay to the thermal state in the same time scale, this is present in both cases. This is the meaning of the okay? So, partial, how much? This is a partial summary. Sorry, I continue.
20 minutes at least.
So this is just a partial summary of this part. So for two harmonic oscillators, we have seen that if you have a common environment, even if they are linear, you can have synchronization. When you have synchronization, we have seen that you have more robust quantum correlations. And we have seen which is the mechanism that is behind this process. It's actually a quite basic mechanism. And now what we want to see is what happens if we go into more complex configuration, let's say. Okay? So we consider the case in which you have a network. So now the network is the system. On the top of the network there is the environment. Okay? So this is the case we are going to consider here. And this would be the case in which the network is representing the case in which the network is dissipating in separate environments. So each node of the network, so these are the coupled oscillators. The different colors represent different frequencies of the oscillators, different natural frequencies of the oscillators. These are the coupling. The thickness of the line is the strength of the coupling. Okay? And here they dissipate into a common, into a separate environment. Here they dissipate into a common environment. And here we can consider another limit case. A case in which you have some object and is actually attached only in one point to some environment. So it's just dissipating locally, let's say. Okay? So this would be just a local bath, local dissipation taking place into the system. And we actually see that even in this case, there would be a kind of limit case for this situation when all these are very different and only one is very important. So this can be the case in which the other are leaking very weakly, and very weakly coupled into the environment, while here there is a very strong dissipation. So this is the scenario in which you can have this local dissipation as a limited exclusion. And we actually find that also in this case you can have an unbalanced damping rate between the normal nodes, and then you can also have quantum synchronization energy. Now the nice thing is that in a system that is a little bit more complicated, two oscillators, you can have that synchronization takes place, and actually that you have it even in the asymptotic case. Something that I didn't comment in the previous plot is that when we were looking at the plots in which there were, for instance, we were seeing there was this discord, and this in the separate path was something like this, so it was decaying quite fast. Okay, while in the case of common bus it was robust. Robust, but we consider that in any case the full system is thermalizing at the end. At the end, also this line will converge to the other. The only thing is that is after such a long time that you have actually something that is more robust, that is robust in terms of time. Okay? Anything is dissipating when you have just two oscillators. This is not the case when you have more than two oscillators. When you have more than two oscillators, you can actually have some normal modes into this network that is completely frozen. So it's not dissipating at all. So it will not thermalize. So at the end, it will remain, it will maintain possibly some stronger quantum correlations, will be different from the thermal state. Is that clear? So this is just the freedom that you have when you have more degrees of freedom. And this is what you have. Typically, if everything decay, for instance, these are just the first order moments of the position of the harmonic oscillators. So they just decay, and then at the end, you just have the oscillator thermalize and you just stop. While here, you have that some oscillation remain present because there is a normal mode that is actually not leaking into the environment. So you continue to fluctuate, to oscillate. So no fluctuate. Okay? So how do we see the synchronization in network? At the beginning, what we see is that we have a network dynamics that is quite disordered due to the difference in the frequencies of the oscillators that you have into the system. And typically, if you just make a random choice of the parameters of your system and you plug it into a common environment, typically you don't have synchronization. So what we can see is what happens if we now take a random network, a completely Nertos-Renier random network, and we just plug it into a common environment, and for instance, we start to tune the frequency of one of the oscillators. And what we actually find is that just by tuning one of the frequency of the oscillator, you can put yourself in the situation in which you have one frozen normal mode, and then in this situation you have actually asymptotic synchronization. So after a random, you will actually have that the network, after a transient, you will actually have that the network synchronized. So these are, for instance, the synchronization. Here there is time, and this is the tuning of the oscillator, the time tuning. So I'm just changing the frequency of this oscillator. So if the frequency is bad, to be clear, you don't have synchronization, but when you approach the proper tuning frequency, you see that synchronization actually raises up. And you have actually a window in which you actually observe synchronization. Okay? So this is what you have. A random network, typically you don't have synchronization, but if you properly tune the network, then you can put yourself in the situation in which you have synchronization. And this would be a diagram. Each red line represents the strength of synchronization between pairs of oscillators. And if here the parameters are chosen in a situation in which you actually have synchronization, and you actually see that after a transient you have synchronization of the full mode. Okay, so this is just a different representation of the same result. So here is the frequency of the oscillator that I'm tuning to put the network in the synchronizing regime. Then I have actually that synchronization occur after a transient. So after a transient, the system, if you have properly tuned the network, synchronizes. Okay, and when you have synchronization, you have also robust quantum correlation. And here the quantum correlation are just measured between pairs of the oscillator network, and then just averaging over, just to have a global view of the amount of correlation that are present between pairs. Okay. So this is some similar result, but when you have, instead of having, now you have the whole network, and instead of having dissipation into a common bus, you just plug the dissipation into one node. So we have one node that is leaking, and under some condition, even in this scenario, you can have that you can actually observe synchronization into the network, always excluding the leaking node. So it's the rest of the network that is synchronizing, not the leaking node. And then if you consider all the other nodes, excluding the leaking node, you have to observe synchronization. Because, of course, any normal mode that is not dissipating into the environment cannot involve the leaking node. So this is the only way to satisfy the condition. You can also, under proper conditions, see if it is possible to synchronize just partially network. So actually here, for instance, we compare the case in which parameters are such that you have synchronization in a cluster but not into the other. Okay? And again, quantum correlation are present into the cluster that is synchronized but not into the other. So even in an extended system, you can just put the synchronization and the quantum correlation just in a piece of it. Okay? Another situation is, let's suppose that you have a network and you want to plug two oscillators. Typically when you plug these two oscillators, even if they are entangled initially, typically they will decohere. But it is actually possible to show that even taking two oscillators that initially are not entangled, under proper condition is possible to entangle them through the network. In the case in which you have it's quite surprising, it's quite interesting. So you take two oscillators, you put them, they are initially in a separable state, and they entangle just because they are coupled through the network. Okay, so this is also something that you can observe in this kind of system. It's always due to the presence of dissipation mechanisms into the network that assist you in the process. Okay, this is just to show the result in this case. And then, just very fast consideration, the situation in which you have asymptotic entanglement is very nicely explained in the simple scenario just with three oscillators. So with three oscillators, you can actually study the role of boundaries, so you can put three oscillators in a line, or you can take something that is a closed triangle, coupling of them, and you can play with the symmetries, so having equal coupling or equal frequency into the edges and so on. And you can actually identify analytically for this simple system which are the conditions that give to you the presence of asymptotic synchronization into the system. So this is a very nice model to study the presence of robust quantum correlation with the reduced number of oscillators. And then another question that could arise is, okay, let's suppose that I have in my system decoherence, but that decoherence is not causing dissipation. It's just giving rise to dephasing in the quantum correlation, but the energy is not leaking out from the system. They're just dephasing due to the presence of noise. Okay? So in these conditions, can I still have synchronization? And the answer is actually no. As we understood before, that the mechanism behind synchronization is the fact that you have some normal modes that is actually disappearing from the system. If you just have dephasing, this is not enough. So we were considering the model of spins now instead of harmonic oscillator and studying the transition between the purely dephasing regime and the dissipating regime, just by changing the way in which the spins were coupled with the environment. And it was actually possible to see that if you have pure dephasing, then you don't have synchronization, while if you have dephasing plus some dissipation, then you can recover synchronization. Okay? And this is the system that was considered. So these are the two spins. They are actually not even coupled between them. They're just coupled through the environment. There is not here, there is just the tuning, not reciprocal coupling that first served. The coupling comes from the environment. And here, in the presence of dephasing, you don't have any synchronization. There is only dephasing. So this was just an overview, a fast overview of other things. This is just an example of unwanted synchronization. I was already showing this at IFISC. It was, I found it, so synchronization typically is a nice and well-explored phenomenon. This was a case and was really undesired. It was in 2012 in San Diego. They were just having a problem for which all the fireworks were just blowing up together. They were perfectly synchronized. And instead of having a show of fireworks that typically lasts maybe half an hour, there was just a 15-second show like this, perfectly synchronized. So this is just a summary of what I've been discussing. So you have been probably seeing in the school, I don't think you have been looking at quantum synchronization in the course of Tchaikovsky. Do you? Did you? No? So it was an extension of synchronization to the quantum regime. to a territory that is quite typically not considered even in the classical case, because these are just harmonic oscillator and all the emphasis is on the coherence and on the way in which energy is lost into the system, from the system into the environment. And we have seen that it is actually possible to have synchronization, that when synchronization is present there are stronger quantum correlation. Is extremely important the form in which dissipation takes place to give rise to this phenomenon. So common versus separate bath and dephasing versus dissipative bath are being considered to show how this is important. And we have been seeing that also in complex configuration and networks you can have actually a quite rich dynamics and quite rich scenario features that can be used. So now I thank you for your attention.
Time for some questions or comments? Yes?
I don't understand the entanglement with two oscillators. No, I just don't understand this part. So if you can explain again.
You don't understand in the sense that you don't know the definition of entanglement, or that you don't understand the relation with synchronization?
Exactly.
Okay, so the entanglement in the case of harmonic oscillators is actually related to the presence of some strong squeezing into superposition of variables that relate the two oscillators. Okay? Now, the fact of having these strong correlations and the fact that they survive when you actually have synchronization is due to the fact that when you put some squeezing initially, some entanglement initially into the system, it can be also squeezing. This squeezing into the fluctuation translates into entanglement, and the squeezing itself survives because it's not thermalizing under the same conditions in which you have synchronization. So telling him in other words, to try to make my point more clear, is not really that synchronization is causing entanglement. It's not a causal relation. It's just that there is something that is happening into the system that is giving rise to both things. The fact that you have something that is not dissipating, that is not thermalizing, maintains both oscillations that are the things that we characterize as the feature of the synchronization, the presence of coherent oscillation, but also the fact that you maintain some squeezing, strong and robust into your system. And this is related to the presence of entanglement. So the physical explanation at the basis, the physical origin of the two features, let's say, is the same. It's the fact that you have something that is not dissipating. Okay? It's clear?
Yeah.
All right.
I think about
More questions? Comments? Please.
Okay, so it's a very easy question, and you said it, but I just don't remember, or maybe I need to rephrase it. So you emphasize the role of the external environment in synchronization. So in fact, it's the key role. So the synchronization is not due to coupling, but due to the third party, which enhances the common modes somehow. So I missed the part. What is the role of coupling then?
The role of
You
coupling,
said at the very beginning that without coupling, they just dissipate and there is no
if
activity.
you don't have coupling, the normal modes of the system are just the two oscillators. It's just this. If you don't have any coupling, and you have two, if they are not coupled, the two oscillators, they will just dissipate independently into the environment. There can be some small correction to the coupling due to there is some kind of line shift coming from the master equation. But apart from neglecting this point, if you just consider the fact that there is no coupling among the two oscillators, they will just dissipate into the environment independently. The normal modes of the system are already the oscillator themselves. It's not making light. So if let's do in the opposite way. Why is it important to look at the normal modes? When you have the normal modes, you just have two independent objects that dissipate into the environment. And then this is easy to treat. Every system is just 1D, okay? And this 1D both in the dynamics and in the dissipation, okay? Let's say.
Okay.
So if these 1D systems, the normal modes that are actually decoupled, they just decohere at different rates
Yes.
when you have a common bound. And one survive, while the other die. Now, this normal mode that is surviving, the point is that this normal mode is, for instance, can be the difference of the position of the two oscillators, is overlapping with the two oscillators. So the fact that the normal modes remains alive means that the oscillators are doing this together or this together. Okay? But if you have that the two normal modes are just the oscillator themselves, they will just die at the rate they want, but it will be typically the same rate, and then you will not have one surviving against the other. The point is that if you have, for instance, two oscillators and two normal modes present, the dynamics of each oscillator is just the sum of the two normal modes under some combination that depends on the initial condition. And this gives rise to the disordered dynamics of the oscillators. This is linear. There is not, it's just the dynamics of the oscillator is just the linear superposition of the dynamics of the two normal modes. Not good enough?
Daniel?
Well, it's very
Just
you don't have any effective coupling through the common path.
Yes, you have a correction. Yes, you have.
Don't have a higher coupling.
Yes.
The common path should be some kind of.
It does.
So it's called the point that.
I don't know if, but even don't know if he's asking in the direction. I mean, the environment can introduce some extra coupling. This is correct. But probably you were just asking what is not visible. Yes, I got it. So the explanation is this. If the two oscillators are just decoupled, they are already two normal modes. They say they're just already decoupled into the dynamics, and they just die each oscillator with its own frequency without caring about anything else and maintaining the same frequency from the beginning. Of course, if the two oscillators were with equal frequencies from the beginning, then they are synchronized. But this is trivial cases.
Yes,
I was wondering, when you reduce your coupling to the common path for a certain mode, is that in the end not reducing the system to a coupled situation of three oscillators?
When you reduce the coupling with the common path,
Dissipation into the bar.
yes, but
you investigate the situation to have non-uniform coupling.
yes.
And for the situation that one coupling is dominating over all the rest, you reduce the problem then to coupling between three oscillators?
No, because what is remaining alive is just one coupling still with an infinite environment, not with just an oscillator. The environment is always infinite in this treatment, yes. Then actually something that we are exploring now is if it is possible to use a finite system, so no environment, and you plug two oscillators into the finite system, and the finite system makes everything, the role of the environment, of the coupling between the two oscillators. We are looking into this. There was actually here Claudio, and there is still here Antonio, and we are looking into that direction. But this scenario is different.
More questions or comments?
Comment in the case in which you can see the common path with some system or.
Typically, the common bus is considered, for instance, when you have phonons or vibrational modes. So if you have, for instance, one can think to have two quantum objects, they can feel the same phonon of the base on the top of which they are. Okay? So if the phonon coherence length is big enough, then you have something like a common path of phonons. So the vibrational modes of the environment can be, in some situation, a common path. The correlation length of the phonon, I don't know. I would like to be able to engineer this, but no idea actually. This is actually nice to come now to the ground in which one really look under which conditions one can see these in a physical platform. And of course, platform in which you have these phonons are, let's say, more easily thought for saying that you can think. But there can be other situations that one can consider. Another situation can be, for instance, if you have two, in the case of spins, there can be two spins into the environment, and they can see a common set of bosonic light modes under some conditions. So also in this case, one could have something similar. But
So the typical situation is separate
typical situation is separate paths. But in solid state physics, they consider a lot of common paths. So the case of the spins that I was showing is just typically considered because of what I was telling before, because they consider a phononic path, and that phononic path very often is treated as a common path. So in the case of spin, it's quite common.
Last question?
Question about correlation. quantity of the clinical configuration in time is the same for different factors, but what am I going to do with this about temperature? How do you look at this kind of things?
If you go to zero, more or less to zero. Yes, in that case, yes. It's again, all the physics is very similar, and simply you have the bath is in the vacuum state instead of being in the vacuum plus some energy. But the physics remain more or less unchanged. I mean, the point is that you always have a bath that has less energy of the initial energy that you put into your system, so still is decaying. Maybe something different with the rising, you take a very hot bath, and then you, instead of dissipating from the environment, you are taking heat from the environment. That's a different scenario. In that direction it will move, but in the other case it will be just the same. Okay.
Okay, so let's thank Roberta again. If someone wants to continue with the tutorial, I will be in the computer room in 10 minutes.
Mucho. ¿Tú lo habías escuchado? ¿Ya?